Let's look at the first example in application of the work energy theorem. So a question reads as follows. A worker pulls a crate of mass 30 kg from rest along a horizontal floor by applying a constant force of magnitude 50 newtons at an angle of 30 degrees to the horizontal. A frictional force of magnitude 20 newton acts on the crate whilst moving along the floor. Now, we are asked to use the work energy theorem to calculate the speed of the crate the instant it reaches point P. Very interesting stuff. So there's critical things that we heard from the statement and we want to put them in application. So we are told that a worker pulls a crate with this force at that angle there. But this crate, he's going to pull it from rest. So at point O, it's at rest. So that means the initial velocity, Vi, is going to be 0 because it starts from rest. That's very interesting. We are also told that it experiences a frictional force which is always going to oppose motion. Remember, this object is moving from O to P, so it means it's going to the right. The frictional force will be opposing motion, so it's going to be to the left. Very interesting stuff. So the first thing to do here is to try and compute a free body diagram showing all forces that are acting on the system. So our object, we represent it as a dot. Because it's got mass, it means it's got weight, so it's got a gravitational force that is always going downward. Now there's a surface, it means there is normal force as well. It's got a normal force, which is the reaction force, which is going upward. Now there is frictional force to the left. We put our frictional force like that. There is also an applied force, but this applied force, it's at an angle. F applied, which is 50 newtons, it's acting at an angle of 30 degrees to the horizontal. That's the complete free body diagram for this question. In an exam question, they would give you 4 marks for it. Now, what's interesting about this? The applied force is at an angle. So it means we can try and find its horizontal component and its vertical component. Let's call this F applied on the X and F applied on the Y. This makes that a 90 degree. So this, you've computed a right angle triangle. You can find F on the X, you can find the force applied on the Y. It makes it easier when you resolve the force into its components. Now, resolving force applied on the X, this angle of interest is adjacent to the F applied on the X, and our force applied is the hypotenuse. So the trig ratio that uses hypotenuse and adjacent is cos. It means our F applied on the X is going to be F applied times cos of the angle 30 degrees, which makes our force applied on the X to become 50 times cos of 30 degrees. So the force applied on the X is going to be how much? Using your calculator, you type there on your calculator. You must always use your calculator to say that 50 times cos of 30 degrees. How much do we get? We get this force to be 43.3 newtons. So this is the horizontal component of the applied force on the X. Now, for the interest of this question, I will not compute the F applied on the Y. This is your work to do at home. Find the component that is on the vertical side. You follow the same logic, you should be able to compute that. Now, remember, we want to find the speed of the crate at the instant it reaches point P. Let's look at this. Now, the next thing that I'm going to do, I'm going to look at the following to say if this object is moving horizontally from O to P, the normal force, the gravitational force, the vertical component of the applied force, all of these 3 forces are perpendicular to the displacement. It means the angle between this force and the displacement is 90 degrees. The angle between this force and the displacement is 90 degrees. The angle between this force and the displacement is 90 degrees. So these forces are not doing work on the system. 1, 2, 3, they're not doing work on the system. The only forces that are doing work on the system is the frictional force, the force applied on the X. Now we are working with the component because we resolved it. And also there was those are the 2 forces actually. Great question. Two forces that are doing work is the force applied and the frictional force. The horizontal component of the force applied is doing work. the vertical component of the applied force is not doing work because it's at 90 degrees to the displacement. So these two forces are the only forces that are doing work on the system. Very interesting. So we can find the net work done on the system. Remember, we said the net work is equals to F net times delta X in conclusion. Now, it means if I want to find the net force here, the right is taken as positive because it's the direction of motion. This is negative because it's opposing motion. It means our net force is going to be force applied on the X minus the frictional force. Now, F net is going to be force applied on the X, the component of the applied force on the horizontal side, minus the frictional force. We were told that, or we calculated the force applied on the X to be 43.3. And we were told in the statement that the frictional force is 20 newtons. So you put your 20 newtons there. Then the difference is going to be 23.3 newtons. This is the net force that is acting on this particular object. So when we have the net force, we can now put it in there. Do we have the displacement? Yes. The object is displaced from O to P, 6 meters. So it means our work net is going to be equal to F net times delta X. Our F net is how much? Our F net is 23.3. Our delta X is 6. We jot that in our calculator and see what we will find. So we go 23.3 times 6 is equals to 139.8. So you've got the net work becoming 139.8 joules. This is the net work done on the object. So what we've done so far, we found the net work done on the object, keeping in mind that these forces are not doing work on the system because they are perpendicular to the displacement. So since we have the net work done, the work energy theorem states that, or we concluded that the work energy theorem states that the net work done on an object is equals to the object's change in kinetic energy. So work net is equals to change in EK. The question says use the work energy theorem. So I cannot use anything else except the work energy theorem. That's why I had to find the net work. To find what? The speed, which is rated. Work energy theorem talks about the speed, which is change in kinetic energy. So let's try and find the speed when it reaches point P. Now, let's delete those guys there. Let's delete those guys and apply our work energy theorem to find the speed when this crate reaches point. So using the work net is equals to change in EK. Let's try and expand that guy. So work net is going to be half of mvf squared minus half mvi squared. So we've got our formula. We know the net work. We know the final velocity. We know the mass. Rather, we don't know the final velocity because that's what we're looking for. We know the initial velocity and the mass. Substituting, we'll have 139.8 is equals to half. The mass of the object is 30. And then Vf squared minus half of 30 times 0 squared. Now this one is very easy because anything times 0 becomes a 0. So that part there is dead. You are left with 139.8 is equals to half of 30 is 15. So you've got Vf squared like that. And then we divide both sides by 15. Divide that by 15, it cancels off. And then we put that in our calculator. 139.8 divided by 15 is equals to 9.32. 9.32 is equals to Vf squared. Now we are not looking for Vf squared, we are looking for Vf.